we are pleased to present a laboratory demonstration of crucial, innovative, clean energy petroleum cleansing technology. This video presentation reveals a unique, innovative, and very timely technology for cleansing petroleum products containing sulfur, nitrogen compounds, and resins with a high degree of efficiency. Most industries have adopted novel technologies to boost productivity and keep up with ever-increasing demands of clean energy. Regrettably, however, the petroleum refining industry lags behind by continuing to utilize methods which can and should be replaced by more efficient processes. The revolutionary method presented in this video of removing mercaptan sulfur from crude petroleum products guarantees that the reduction of the total sulfur content and tar of straight-run petroleum products of low-quality heating fuels is reduced to lower than the level in Euro 5 standard motor fuel. The effect of utilizing the reagent, which is a proprietary chemical compound developed by the Society of Creative Scientists in Eastern Europe, applied in a novel technology of purifying diverse petroleum products, as will be demonstrated, results in a highly effective purification of light oil products from sulfur and nitrogen containing compounds by oxidative complex formation. Three samples of widely used light oil products have been selected to demonstrate the extraordinary effectiveness of the newly invented substance. Straight-run gasoline, commercial gasoline AI-92, commercial diesel fuel. To start the process of purification, 0.2 milliliters of the reagent, our purifying chemical substance, is added to each of the samples to be purified. After consistently shaking the container which holds the petroleum product being purified, we review the reaction of our chemical substance in interaction with sulfur and nitrogen compounds. The purification process is continued by periodically shaking the container holding the petroleum product and our chemical substance for the duration of the main experiment, which extends for approximately 15 minutes. The dynamics of the reagent are continually being observed. A straight-run fraction of gasoline in the quantity of 400 milliliters is utilized during the main experiment. The gasoline is poured into the reactor equipped with a bubbler. A back condenser is installed to capture the light fractions that are removed during the flushing. The reagent, in the amount of 4 milliliters, which is measured in the cylinder, is placed in a drip funnel and set in the upper part of the installation container. To intensify the process of mixing and activating the oxidative complexion with oxygen of the air, a supply of atmospheric air is infused. A crane is used to obtain a constant rate of delivery of the reagent into the reactor, while observing the changes occurring with the sample of fuel in the reactor. The processes of fuel purification observed in the reactor in the currently known methods occur during a reaction called catalytic hydrocracking or hydrotreating, with the huge difference that the presently used industrial method for cleaning the same product, gasoline, it involves the necessity to increase the pressure in the reactor vessel to 5 megapascals. Loading a complex catalyst with a limited lifespan because of sulfur poisoning raising the temperature to 400 degrees Celsius. And then rinsing the hydrogen-containing gas in a volume of 100 liters for the fuel quantity, and it's demonstrated in this experiment. The cleansing process clearly shows how the reagent interacts with sulfur and nitrogen-containing compounds and resins in the fuel under normal conditions, and transforms these undesirable components into a water-soluble resin-state acid tar. This proposed method is significantly superior to the antiquated method presently being used. It is able to replace the cycle of catalytic hydrocracking and hydrotreatment. After 20 minutes, we stop the cleansing process to wash the fuel from oxidized forms of sulfur and nitrogen-containing compounds. For this process, the content of the reactor is transferred into a glass container to which 400 milliliters of water is also added. Under intensive stirring, the acid tar residues, which are left in the fuel, now become water-soluble complexes passing into the water phase. As an example, we demonstrate the water solubility of the acid tar that remains in the reactor containing water. To separate the phases, the contents of the glass are transferred into the separating funnel. After separating the phases, the lower water layer is drained. To remove the residues of water impurities and residues of acidic complexes, the final cleaning of the fuel is accomplished by passing it through any of the sorbents. In this case, aluminum oxide is used. We summarize the visual analysis of the finished product with referenced fuel samples. In all three control samples of widely used light oil products, there is evidence that through the application of our technology, the purification process of the fuel results in formation and elimination of sulfide complex. This presentation clearly demonstrates the great technological advantage and financial benefits of our proposed and novel method, especially as compared to the existing methods used by refineries. We are prepared to present a demonstration of this unique method to any serious petroleum producing company that desires to greatly augment their productivity, efficiency, and increase their product quality, resulting in significant economic growth. For questions or for further information, please contact the Society of Creative Sciences, which are the proprietors of this intellectual property.